Hello, my dear friends. We have already completed one of the important chapter of this unit is multiplexer, demultiplexer, decoder, 7 segment units, ROM, etc. and exclusive OR gate, etc. So the logic circuit design chapter is completed. Now we are going to take some another part of this unit. That is the second chapter related with the clocks and triple five timer circuits. What is the clocks and triple five timer circuits? It's a very important in the digital circuits. And the objective of study this chapter is this. The objective of this clocks and timer is this. State the purpose of a clock in a digital system and demonstrate an understanding of basic terms and concepts related to the clock waveforms. Second objective, discuss the operation of Smith trigger and its application. Smith trigger is another very important circuit which converts a rake type or a noisy signal into perfectly a clock waveforms or a train of the pulses. It converts, and that's why that can be utilized given as a clock waveforms for any digital system. That's why Smith trigger is that much important. Then we are going to study about the two important circuits using a triple five timer, that is astable and monostable multivibrators, and compare their behaviors of these two circuits. Then we are going to study a different IC which is available, which is known as retriggerable or a non-retriggerable monostable. So monostable also can be a retriggerable. That means during the same trigger pulse, it can be triggered again and again, or during that pulse, it cannot be re-triggered again by giving a trigger pulse. That is called retriggerable and non-retriggerable. So that concept also we are going to study here. Now, what is the role of digital clock? The heart of every digital system is the system clock. Just like in our body is functioning because of the heart. It provides the heart pulse beat. Similar way, every digital system is working because of the clock waveforms, because it synchronizes everything and digital system. Without a digital clock, the system will be stopped or it will not be working. That's why the system clock is known as the heart of every digital system. The system clock provides the heartbeat without which the system will cease to function. In this chapter, we consider the characteristic of digital clock signal as well as some typical clock circuits. So, what is the exact characteristic of ideal clock signal that we are going to study particularly in this chapter and in this particular lecture? Then there is a Smith trigger are used to produce nearly ideal digital signal, ideal digital rectangular waves from otherwise noisy or degraded signals. Propagation delay time is propagation delay is the time required for a signal to pass from the input of a circuit to its output. We have also studied about the propagation delay time earlier. What is that? Propagation delay time is the time required that output is changing from one state to another state after the input have been applied. It is not happening instantaneously. It takes time. So you can consider like that propagation delay is the time required for a signal to pass from the input of circuit to its output. You will see how to utilize logic gate propagation delay time to construct a pulse forming circuit. We need a positive pulse as well as we need a negative pulse to trigger some of the digital system. And for that, the pulse duration must be very small. That means it is in the order of nanoseconds. And the propagation delay time of a digital gate, maybe the NAND gate, NOR gate, etc., is also in the order of nanoseconds. So, using that propagation delay time, we can prepare a pulse forming circuits. A monostable is a basic digital timing circuit that is used in a wide variety of timing applications. To undergo a various project or to prepare a digital system, you need a monostable, and that is utilized as a digital timing circuit. In so many timing applications, it is required. It is triggering the circuit. It makes the automation. It requires in microprocessor. It requires in the industry to trigger something, control circuit, etc. We consider a number of different commercially available monostable circuits and examine some common applications. In the market also, so many commercially ICs are available which contains the monostable circuit because of its wide variety of application in the industry, and that's why monostable are ready-made available in a form of IC in so many ICs. Clock waveforms. So now we are going to study what is exactly clock waveforms. Clock, you know that the normal meaning of the clock means it synchronizes our system. We start from the morning to evening, and everything we are relating with the clock. That 10 o'clock there is a college, 11 o'clock this lecture will be there, 12 o'clock this lecture is going to be finished, etc. So our body cycle and our actually routine is synchronized with the clock. The same function, these waveforms are going to be there in digital system. That's why it is named as a clock waveforms. Up to this point, we have been considering a static digital logic level, that is voltage level that do not change with the time. So until now, for a conventional digital circuit, that may be a, you can say that combinational logic circuit like a AND gate, OR gate, NOT gate, etc. What kind of input you are giving? Input you are giving a binary, either 1 or 0. Binary 1 corresponds to plus 5 volt and binary 0 corresponds to 0 volt. This is in a positive logic. Similar way, there is a negative logic also. But that means whatever 1 0 you are giving, or high level input or low level input you are giving through the switch. That means switch is in one position, there is a constant DC voltage, high level is going to be there. Where the switch is going to be in another position, it is constant 0 volt DC is there. That means manually we are giving a stable voltage level for 1 and 0 conditions or high or low conditions. So this kind of things you have studied. Now instead of that, we are going to study that okay, the input which we are giving is not in the form of DC voltage, but it is in the form of AC voltage. That means the voltage level is continuously changing. It may be for certain period of time high, and then automatically for certain period of time low. Again it is going to be high, and this cycle is going to be repeating. That is called a clock waveforms. However, all digital computer systems operate by stepping through a series of logic operations. The system signals are therefore changing with the time, they are dynamic. So we are going to give now the signal instead of stable levels, we are giving a dynamic level. That means automatically they are repeating that cycle for certain period. Let us say for the T1 it remains to be high, and then for a certain period, that is time T2, it remains to be low, and this cycle is going to be repeating after completing this cycle automatically. It is a clock signal that advances the system logic through its sequence of steps. That means in digital system, everything is going to be in sequence. That means one instruction is going to be executed, then the next instruction is going to be executed, then the third instruction is going to be executed. That means everything is going to be happening in sequence. And this can be happen in automation or by itself, that is going to be seen by clock signals. That means when the first clock pulse is going to be there, first instruction is going to be executed. Then after, when the second clock pulse is going to be hit the system, then the second instruction is going to be executed, and that way it's happening in sequence of steps. The clock and timing circuit square wave are shown in figure 7.1a. Is the typical clock waveforms used in a digital system. It should be noted that clock need not be a perfectly symmetrical waveforms shown. So here this is the figure. You can see that. Here this is the figure 7.1. This is the figure related with the ideal clock waveform. You can see that this is a train of the pulses is coming here. So this is almost a level. During from here to here, the level is going to be low. From here to here, the level is going to be high. Again, from here to here, the level is going to be low. Again, it is going to be high. Again, it is going to be low. So this kind of pulses are coming continuously. That is called a clock cycle. Now, time during which it is going to be high, we can designate it is going to be T1. So from here to here, during this time interval, that is T1, it remains to be high. From here to here, for this time interval, it remains to be low. Let us consider it is going to be T1, T2, sorry. And T1 plus T2, that means it is going to be total clock cycle time. And this cycle time is going to be repeating. Now, if you see this waveform A, here time t1 is equal to time t2. That means t1 is equal to t2, time during which it remains high and time during which it remains low are equal. And that's why this kind of waveform is known as a square wave, or it is known as a symmetrical waveform, or we can say that it is having a duty cycle of 50%. It need not be always symmetrical waveform or square wave is required as a clock waveform. It can be like this also. This is also perfectly acceptable. You can see that here time during which it is going to remain high T1 is different, and time during which it remains low it is going to be different. T1 is less than T2. That means T1 and T2 are not going to be equal. This kind of rectangular waveforms are also acceptable. This is also known as the asymmetrical waveforms, or asymmetrical waveform is also acceptable. Only the main requirement is that the clock waveform must be perfectly periodic. That means this period should remain constant for certain period of time. That means it should not change. The frequency of the clock waveform should be stable. That is very, very important characteristic of the clock waveforms. It could simply be a series of positive or negative pulses as shown in the figure. In this particular case, it is shown a positive waveform. That means low level is corresponding with the 0 volt and high level is corresponding with the plus 5 volt. So this is called a positive waveforms or positive pulses here or here also. But if it is passed through the inverter or a NOT gate, you will get a negative level. That means the time during which it is going to be high will be more, and time during which it is going to be low will be less. So just complement of this signal or mirror image of this one is called a negative pulses. The waveform could be, of course, be considered an asymmetrical square wave with a duty cycle other than 50%. So if it is a rectangular or asymmetrical waveforms, then duty cycle is not going to be 50%, but it may be other than 50%. It may be more than 50% or it may be less than 50% because T1 and T2 are not same. The main requirement is that the clock be perfectly periodic and stable. That is important. Notice that each signal in figure 7.1 define a basic timing interval during which the logic operation must be performed. This is very, very important. So, what is the basic timing interval? That is nothing but clock cycle time. So, in a digital system, any operation is going to be performed. That operation, either it is going to be logical operations or it may be arithmetic operation. That operation must be completed before one cycle of the clock is going to be over. That means when the second clock pulse comes, before that, the logic operations must be performed. That is basic need. And depending upon that, how the system is going to be faster, that is decided. When you are selecting either laptop or a mobile phone or any digital system, you see that what is your clock frequency or at which frequency it is going to be operating. So if it is operating with the clock frequency higher and higher, that means basic time interval is going to be smaller and smaller, and that way the logic operation is performed very faster and faster. That means system becomes more and more faster. We are updating our versions with this important characteristic, or with this aspect we consider that what should be the cost of the mobile, and with that we are purchasing that mobile. The basic timing interval is defined as the clock cycle time, and it is equal to one period of a clock waveform. Thus, all logic elements must complete their transition in less than one clock cycle time. That means when the one clock cycle time is periodic time of the clock pulse is going to be finished, before that the logic operation must be completed. Synchronous operation. Nearly all of the circuits in a digital system, computer, changes the state in synchronism with the system clock. A change of the state will either occur as the clock transition from low to high or as it transition from high to low. That means normally nowadays the transition is must require. So the clock period which is changing from low to high or high to low, that means when there is a transition of the state of the clock signal which hits the system, then something is going to be happen in the circuit. When the level of the clock is either low or high, nothing is going to be happen or it is inactive. That is the meaning of this. So a change of the state will either occur as the clock transition from low to high or as its transition from high to low. The low to high transition is frequently called the positive transition (PT), as shown in the figure 7.2. The PT is given emphasis by drawing a small arrow on a rising edge of the clock waveform. So, like this arrow, which indicates that the circuit will respond when the clock pulse is changing its level from low to high. That means on a positive transition, circuit is going to be responding. On negative edge, that kind of circuit is not responding. There may be another circuit which may be negative edge triggered. A circuit that changes the state at this time is said to be positive edge triggered. The high to low transition is called the negative transition, as shown in the figure 7.2. The negative transition emphasizes by drawing a small arrow on the falling edge of the clock waveform. That means when the clock level is changing from high to low, that transition is called the falling edge of the clock waveform, and that time the arrow is shown by this kind of arrow. That means down arrow will be there, and this kind of circuits are responding to the negative edge trigger. Virtually all circuits in the digital system are either positive edge triggered or negative edge triggered, and thus synchronize with the system clock. So the normally we design the logic circuit may be either positive edge triggered or negative age trigger, and they are going to be synchronized with the clock waveform. That means when that negative age is going to be occur, the instruction execution will start and it will be finished before the next negative or positive age of the clock pulse. And that way it is actually uh, consider that basic time interval during which the logic operation is going to be completed. There are few exceptions. For instance, the operation of a push button. Sometimes manually also you can operate or you can trigger the circuit by push button by a human operator might result in an instant change of the state that is not in synchronism with the clock. This is called asynchronous operation. So sometimes if you don't give the clock or you can trigger the circuit manually by using a push button switch, that is also possible, but it is called asynchronous operation. Now, we will find out what is basic time interval. Basic time interval is nothing but the periodic time. So related with that, there is a small example. What is the clock cycle time for a system that uses either a 500 kilohertz clock or an 8 megahertz clock? The solution. The clock cycle is simply one period of the clock. For a 500 kilohertz clock, one cycle time t is equal to 1 upon f, that is equal to 1 upon 500 into 10 raised to 3 hertz, that is equal to 2 microseconds. So you can consider that clock cycle time or basic timing interval here is going to be 2 microseconds when it is operating with the 500 kilohertz, and when it is operating with the 8 megahertz, that is going to be converted from microseconds to nanosecond, 125 nanoseconds that you can see here. Now we are going to study about the characteristic of an ideal clock. The clock waveform drawn above the timeline in figure 7.3a is a perfect ideal clock. What exactly are the characteristics that makes up an ideal clock? First, the clock level must be absolutely stable. So now we are going to study about the characteristics of an ideal clock. If there is an ideal clock is there, what are the characteristics? There are basically three characteristics. Stability of the level. Absolute stability of the level is very important. So the first characteristic is absolute stability. Second characteristic is the transition time. And third characteristic is the frequency stability. One by one, we are going to study this stability characteristics. So clock waveform drawn above the timeline in figure 7.3a is the perfect ideal clock. What exactly are the characteristics that makes up an ideal clock? First, the clock level must be absolutely stable. When the clock is going to be high, the level must hold a steady value of plus 5 volt as shown between points A and B on the timeline. When the clock is low, the level must be unchanging 0 volt as it is between point B and C. In actual practice, the stability of the clock is much more important than absolute value of the voltage level. This is important. You see this waveforms. Here, this is the clock waveforms. A ideal clock waveform is there. This is the timeline, and here the timeline is shown. A instant when the level is changing from low to high. So before the time A, it is level is low, and it corresponds to voltage level of exactly 0 volt ground potential. And at instant A, it is going from 0 to 1. That means the level is changing from 0 to 5 volt. And then it remains from A to B time. That means during this interval T1, it remains to be in high state, exactly 5 volt. That is corresponds to logic 1. Again, between B to C, it remains to be low, that is T2 time, it remains to be in a low state, and that is going to be 0 volt. But exactly here it is going to be 5 volt. But what is the requirement is this. This is absolute level of 5 volt. But even if it is not exactly 5 volt, if it is 4.8 volt, that is also perfectly acceptable if that voltage level is perfectly stable, unchanging. That means with respect to time, this level is absolutely constant, not changing. It's not changing like this way. It is not fluctuating 4.7, 4.6 or 4.9, 5.1. It should not be fluctuate like this way. Whatever that voltage level is there, that should be exactly stable and unchanging with respect to time. Between B to C, it should be exactly 0 volt. Even if it is zero point 0.2 volt, it is acceptable. But it should be unchanging 0.2 volt only. That is important. We'll see that how the waveforms are going to be seen on oscilloscope, and it is like this two horizontal traces will be there. Vertical line is going to be missing, or it is not going to be visible on oscilloscope because oscilloscope will not be responding. For instance, it might be perfectly acceptable to have a high level of plus 4.8 volt instead of plus 5.0 volt, provided it is steady, unchanging 4.8 volt. The second characteristic deal with the time required for clock levels to change from high to low or vice versa. So this first characteristics deal with the stability of the level. That means level stability is very much important. And second characteristics deal with the time required for a clock levels to change from high to low or vice versa. The transition of the clock from low to high at point A in figure 7.3a is shown by a vertical line segment. This implies that at instant of time A, level of the clock is changing from 0 to 1, and that is called positive age. And how much time is required? This shows that it is exactly vertical. That means with respect to timeline, time delta t is going to be 0. That means changing level from low to high, it is instantly happening. This implies a time of 0. That is, the transition occurs instantaneously. It requires a 0 time. The same is true for a transition time from high to low at point B in figure 7.3a. Thus, the ideal clock has a 0 transition time. So this is second characteristic. Ideal clock must be have 0 transition time, but in actual reality, it is not going to be there. But if it is minimum, that is desirable. A nearly perfect clock waveform might appear on oscilloscope trace as shown in the figure 7.3b. At first glance, this would seem to be two horizontal traces composed of line segments. On closer examination, however, it can be seen that the waveform is exactly like the ideal waveform in figure 7.3a if the vertical segments are going to be removed. So whatever the figure A is there you can see the vertical line segments. But on oscilloscope, it is not seen because of the limitation of the oscilloscope. The vertical segment might not be appear on the oscilloscope trace because the transition time are so small, nearly zero, and the oscilloscope is not capable of responding quickly enough. That means it is not synchronized or it is not going to be responding the transition time from low to high very fast. So the oscilloscope limitation, it is not going to be traceable. The vertical segment can usually be made visible by either increasing oscilloscope intensity or by reducing shift time. But it can be visible by increasing response of the oscilloscope, that is by increasing the intensity of the oscilloscope screen or reducing the shift time. That means response time becomes better, and then it can visualize the vertical line segments. Figure 7.3a shows a portion of the waveform in figure 7.3b, the expanded by reducing the sweep time such that transition times are going to be visible. Clearly, it requires some time for the waveforms to transition from low to high. This is defined as rise time. So, when the level is changing from low to high, the amount of time required is called a TR, that is rise time. Remember, the time required for transition from high to low is defined as the fall time, TF, and it is designated as TF, fall time. It is customary to measure the rise and fall times from points on the waveform referred to as 10% and 90% points. In this case, 100% level is changing from 0 to high volt. So 10% of this is 0.5 volt and 90% is plus 4.5 volt. Thus, the rise time is that time required for the waveform to travel from 0.5 volt up to 4.5 volt. Similarly, the fall time is that time required for the waveform to transition from 4.5 volt down to 0.5 volt. That means when it makes a transition from 10% to 90%, the time required is called T rise time. And from 90% to 10%, waveform makes a transition, that is called fall time. Finally, the third requirement that defines an ideal clock is its frequency stability. The frequency of clocks should be steady and unchanging over a specified period of time. That means the clock frequency must be stable, but it cannot be stable indefinitely. There are two different ways we have defined that it requires a short-term stability and it requires a long-term stability. The frequency of the clock should be steady and unchanging over a specified period of time. Short-term stability can be specified by requiring that the clock frequency or its period not to be allowed to vary by more than given percent over a short period of time, say few hours. Because when we perform some experiment, when we utilize some circuit for certain periods, maybe laptop or maybe our practicals or maybe some circuitry which is going to be on for certain hours only, then the clock frequency is required to be stable for that much period only, and that is called short-term stability. Clock signal with short-term stability can be derived from straightforward electronic circuit as shown in the following section. So, short-term stability can be derived using a clock frequency generator using small electronic circuits only. Long-term stability deals with the longer period of time, perhaps days, months, or years. So, some of the circuits will remain continuously on. That is going to be remains on for some days, some months, or some years continuously. And frequency of the clock period should not be changed for this much time, and that is called long-term stability is required. Clock signals that have long-term stability are generally derived from rather special circuit placed in a heated enclosure. How that can be derived? Using that clock generator or system clock which is to be prepared from the circuit. That circuit should be placed in a heated oven or which keeps the temperature of the circuit constant, and that way that Q level of the transistor does not change, and hence the frequency does not shift over a long period of time, and that way the long-term stability can be derived. The clock signals that have a long-term stability are generally derived from rather special circuits placed in a heated enclosure, usually called a oven, in order to guarantee a close control of the temperature, and hence its frequency can be controlled or it can be stable. Such circuits can provide a clock frequency having a stability better than few parts in 10 raised to 9 per day. So per day, even the frequency is in the order of gigahertz, 10 raised to 9 corresponds to gigahertz. Only few parts of the frequency, few percent of the frequency is allowed to vary. over a day or over a month. So that is important. Thank you very much, friends.